Welcome to this explainer. If you've been building AI products lately, you've absolutely heard the term embeddings tossed around. People talk about it like it's some kind of magic black box of floating numbers, right? But as product managers, we literally can't afford to build on magic. So today, we're taking that black box and transforming it into a practical, actionable product strategy. We're going to demystify embeddings from first principles, giving you exactly what you need to make smart, informed decisions about your AI features. Let's get into it. Okay, right out of the gate, here is your golden rule as an AI product manager. If your product needs to compare items, or if it needs to actually understand the meaning behind what a user types, embeddings win. That's it. Whenever similarity matters, whether you're fetching a relevant document, recommending a new song, or matching a photo, this is the core technology you're going to rely on. So here's our roadmap for today. First, turning meaning into math. Second, we'll go inside the latent space. Third, embeddings in AI products. Fourth, choosing an embedding model. And finally, managing the trade-offs in production. Let's start with section 1, turning meaning into math, and the paradigm shift in data retrieval. Think about how things used to work. For decades, traditional relational databases totally relied on exact match lookups. If your user searched for download, the system used a B-tree index to find the exact word download. Simple, right? But what if your user types export or backup instead? Traditional keyword search completely fails because the characters don't match. Semantic search, which is powered by embeddings, changes the game entirely. Instead of matching characters, it performs a similarity search based on actual human meaning. To pull that off, we have to somehow turn that meaning into math. And this brings us to vectors and tensors. Now, don't panic. In machine learning, a vector isn't about physical direction and magnitude, like you might remember from high school physics class. It's way simpler. It's just a one-dimensional tensor. Basically, a numerical list or an array that represents the distinct features of your data. A tensor is really just the generalized term for this mathematical bookkeeping device. So at the end of the day, an embedding is just unstructured data, like a word or a picture, transformed into a big list of numbers. To visualize this, imagine projecting the words bird, dog, and fly into a shared space. The absolute magic property here is that spatial distance literally equals semantic dissimilarity. Bird and fly are going to cluster close together because they share a lot of semantic context. But dog? It's chilling much further away. We've taken abstract concepts and turned them into measurable coordinates. Moving on to section 2, inside the latent space. Let's navigate these hidden dimensions. So what exactly is this space we're talking about? It's called the latent space, and it's basically a compressed, lower dimensional representation of your data. Instead of forcing the AI to process millions of raw pixels or raw text files, the model learns to map data into this latent space where similar items naturally group up. The word latent just means hidden. These features aren't explicitly labeled by human engineers. The neural network discovers them on its own during training. It's kind of like describing a car. You don't describe every single atom or pixel, right? You just capture its carness, the color, the shape, the brand. Latent space dramatically shrinks your data size while perfectly capturing that essential carness in just a few hundred numbers. Now, how do we actually measure the distance between those numbers? Well, the mathematical ruler you choose dictates exactly how your product interprets similarity. Cosine distance measures the angle between vectors, which is fantastic for natural language because it normalizes the magnitude. Euclidean distance measures the straight line distance, making it super sensitive to magnitude or counts. And dot product? It combines both angle and magnitude. As a PM, you absolutely need to know this because your choice of metric literally changes the search results your user sees on their screen. All right, section 3, embeddings in AI products. Let's take this theory and turn it into features. The type of input data you have completely dictates the model you need to use. Say you're embedding sentences for a semantic search feature, or maybe a RAG application. You're going to look at models like sentence BERT, which usually output around 768 dimensions. But what if you're building a visual search feature to let users match photos? Then you'd pivot to multimodal models like OpenAI's CLIP. Building user or product recommendations, you might rely on matrix factorization. The takeaway here is that different inputs require totally distinct architectures. There is no one-size-fits-all. And here is how all of this builds into a complete, living system. This right here is the full lifecycle architecture of a recommender system. Notice that it is not just a single simple API call. As a PM, you own this entire flow. It starts at the offline data store, feeds into a candidate generator to create your embeddings, stores them in a highly optimized vector database, and ends with real-time inference and ranking the second a user opens your app. And every single step in this pipeline introduces its own latency, cost, and complexity that you have to manage. Which perfectly leads us into Section 4, choosing an embedding model, and the PM decision framework. Here is your step-by-step roadmap for picking a model. Step 1, identify your specific use case and modality. Are you working with text, images, or both? Step 2, select a baseline model using the MTEB leaderboard. That's the massive text embedding benchmark, which tracks state-of-the-art performance. Step 3, import your specific domain data. And step 4, you have to evaluate the performance using metrics like precision, recall, or NDCG. You cannot just blindly trust a public benchmark. You absolutely have to run custom evaluations on your own dataset to find the right balance between latency and accuracy. Let's compare some real-world trade-offs to show you what I mean. OpenAI's Text Embedding 3 Large gives you massive 3,072 dimensional vectors with top-tier accuracy, but you're paying a premium of 13 cents per million tokens, and you inherit their API latency. Cohere is fantastic if your product needs strong multilingual support. But take a close look at Sentence Transformers. It's an open-source 384-dimensional model. Sure, the accuracy drops slightly, but inference latency is a lightning-fast 8 milliseconds on a standard CPU, and you pay zero API costs. For high-volume, massive-scale apps, choosing a self-hosted model like that is exactly how you save your margins. Finally, Section 5, managing the trade-offs. This is the reality of production. Let's break down the hidden costs that can sneak up on you. Querying cost is tied to API availability. Indexing cost hits you upfront when you process your massive document libraries. But pay very special attention to storage and search latency. Storage cost scales linearly with the dimension of the embedding. A 3,000-dimension vector takes up vastly more memory in your vector database than a 256-dimension vector. And guess what? Your search latency grows right alongside it. Higher dimensions definitely mean better semantic nuance, but they directly inflate your memory bills and slow down your user response times. But there's good news. To combat this bloat, the industry is moving toward cutting-edge techniques like Matryoshka representation learning, or MRL. Just like a Russian nesting doll, models trained with MRL enforce a layered structure. The most critical semantic information is front-loaded right in the core of the vector. This means you can essentially chop a massive 3,000-dimension vector down to a smaller 256-dimension doll and still retain incredibly high retrieval performance. For a PM, this is a total game changer. You can drastically cut storage costs in your database without losing the retrieval power your users expect. Before we wrap up, I need to issue a massive warning about system maintenance, the danger of embedding drift. Look, if a shiny new model hits the MTEB leaderboard, you might be tempted to just swap it in, right? But remember, embeddings from different models are not comparable. Swapping your query encoder without completely reindexing your entire database changes the neighborhood structures in your latent space. The new model might be objectively stronger on paper, but it could unpredictably alter how your specific domain language clusters, which will completely tank your RAG retrieval accuracy. So the crucial takeaway is this: embeddings are a foundational product commitment. They are not just a plug-and-play feature. I want to leave you with a provocative thought to challenge your team with tomorrow. If you upgraded your query encoder today, how exactly would embedding drift break your enterprise RAG system's memory? Think deeply about your evaluations, your versioning, and your infrastructure. Thank you so much for joining me on this explainer. Keep learning, and I'll see you in the latent space.